Hello guys, this is Modi. Today I want to tell about my topic, uh, helium cooling so near absolute zero in thermodynamic limits. Helium plays a major role in central role in reaching extremely low temperatures closer to absolute zero than any other known method. The unique properties of helium, particularly in quantum mechanical behavior at low temperatures, make it indispensable in cryogenics. Cooling to near absolute zero enables to study of quantum phenomena and superconductivity. This presentation explores the thermodynamic limits and challenges involved in helium-based refrigeration. Absolute zero and its meaning. Absolute zero defined as 0 Kelvin or minus 272.15 degrees Celsius represents the theoretical point where all classical motions of par- partial changes it is an asymptotic limit that cannot be reached in practice due to thermodynamic constraints. According to the third law of thermodynamics, reaching absolute zero is impossible through finity process. Understanding thermodynamic principle guides the development of ultra-low temperature cooling techniques. And the challenges of reaching absolute zero, according to the third law of thermodynamics, as a system approaches absolute zero, its entropy approaches a minimum and the energy required to remove additional heat increases dramatically. This makes reaching zero Kelvin impossible, but one can come infinitely close. The next one is helium as a coolant. Why helium? Means helium remains liquid at temperatures where most substances freeze solid. Even at absolute zero under normal pressure, helium does not solidify, but it becomes a superfluid due to quantum effects, allowing continuous cooling below 1 Kelvin. Helium reaches liquid at temperature close to absolute zero, unlike other gases that solidify. The weak interatomic forces in helium facilitate its uses in cryogenic applications. Helium's low boiling point is around 4.2 Kelvin at temperature, atmospheric pressure, makes it ideal for refrigeration. Helium exists in two stable isotopic forms, helium-4 and helium-3. Each isotope has different nuclear properties, resulting in distinct behaviors at low temperature. These differences are exploited in advanced refrigeration techniques. Helium-4 and superfluidity below 2.17 Kelvin to helium-4 transitions into a superfluid is known as helium-2. In this space, it exhibits zero viscosity, allowing it to flow without friction, a phenomenon deeply tied to Bose Einstein condensation. Helium-3 and quantum properties. Helium-3 being a terminal behaves differently. It becomes superfluid at much lower temperature, around 2.5 millikelvin. The pairing of helium-3 atoms resembles copper pairing in superconductors. A purely quantum mechanical effect, and the Joule-Thomson expansion is a common process for cooling helium to cryogenic temperatures. Adiabatic demagnetization and dilution refrigeration are advanced techniques for reaching millikelvins regions. Each method leverages helium's unique physical properties to achieve progressive lower temperature. Helium cooling begins with liquefaction using the Joule-Thomson effect and successive progressive expansion cycles. Helium gas is cooled until it condenses at around 4.2 Kelvin at atmospheric pressure. The Joule-Thomson effect, when a gas expands without exchanging heat with its surroundings. Its temperature changes depending on intermolecular forces. Helium's Joule-Thomson coefficient is small, requiring pre-cooling before effective liquefaction. Pre-cooling with other trigonants. Before helium liquefaction, nitrogen or hydrogen is often used for pre-cooling. Liquid nitrogen cools the system to about 77 Kelvin, greatly reducing the energy required for helium liquefaction. Helium refrigeration techniques. Dilution refrigeration exploit the mixture of helium-3 and helium-4 to reach millikelvin temperatures. The process involves continuous circulation and separation of isotopes at low temperatures. This method is usually for experiments in quantum physics and low temperature physics research. Modern helium refrigeration uses a combination of mechanical compressors, expansion valves, and heat exchangers arranged in closed cycle to produce a maintain extremely low temperature. In the next, thermodynamic limits and challenges. The third law of thermodynamics impels absolute zero cannot be physically attained, only approaches asymptotically. Heat leaks rigorously entrope and material limitations impose practical thermodynamic boundaries. Overcoming these challenges requires advanced insulation and numerical systems design. Quantum effect at near zero Kelvin. Quantum phenomena such as superfluidity, Bose-Einstein condensation energy near absolute zero. These effects provides insights into fundamental physics and functional technical applications. Achieving such as conditions demands precise control of thermodynamic particles. Applications of helium cooling. Helium cooling is crucial for superconducting magnetic in MRI and particle acceleration. It enables the operation of quantum computers and sensitive detectors. Research in condensed matter physics relies heavily on helium-based refrigerations. Future directions in helium. 。  . 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 . . 。 . . . 。 . 。 . . 。 . . 。 。 . 。 . 。 。 . . 。 . 。 . . . 。 . . 。 . 。 . Advances aim to improve efficiency and reduce costs of ultra-low temperature system. Novel materials and techniques may extend the thermodynamic limits further. Research continues into alternative cooling methods and isotopic enhancement. Conclusion and outlook. Researching near absolute zero with helium is a triumph of thermodynamics and engineering. Ongoing researches aims to overcome current limitation and explore new quantum phenomenon. The pursuit of ultra low temperatures continues to expand our understanding of the universe at its most fundamental level. Thank you.